ladies and gentlemen. How are you? Good. That's great. Welcome. I'm Simon Gage, Director of the Festival. Welcome also Jocelyn and Andrew. It's very good to see you here. Before we start, I would just like to acknowledge a little bit of support we've had with organising this from two organisations that have been fighting the corner of science for many years. The Royal Society since 1660, doing great things for science, and of course our own Royal Society of Edinburgh. So thank you. I acknowledge the support in making this happen. That's great. Joined by two delightful people, interesting people. Of course, the wonderful Jocelyn, no stranger to the Science Festival. In fact, recipient of the Edinburgh Medal some years ago. Maybe that will come up in conversation, I don't know. And Andrew Cohen, who's head of science at the BBC, responsible for bringing us many delightful programs like Horizon, I think, and the wonders of the universe. Yeah. All the wonders. He's responsible for all wonders.
Few wonders.
At the BBC. Well, we were joking earlier about what I might call him. I may just head of wonders from now on. So please welcome them to Edinburgh. Welcome them to the Science Festival.
Hello, everyone. Very good to be here. I should say at the start, really, absolutely honoured to be chairing this session, Jocelyn. So very, very pleased to have been invited. Just to give you an idea, we're going to talk for about 30 to 40 minutes, and then we're going to open up to questions at the end. So please do store up your questions. We'll try and get as many of those in as possible. And we're going to work our way through most of your life, I think, is the plan, if that's okay, Jocelyn.
70 years in 35 minutes, yes.
Okay, so we'll do our very best. But we're going to start by jumping in at the deep end, if that's okay. And I'm going to ask you, you're responsible for one of the greatest discoveries ever in astronomy, the neutron star. And I'm going to ask you just to start off just by taking us to one of these stars, describing what we'd see. What is it?
You'd actually have trouble getting there alive, is the first thing to say. These things have very strong gravity. They also have a very strong gradient of gravity, which means as you're coming into land, the force on the lower part of your body is a lot stronger than the force on the upper part of your body. But assuming somehow you defy that and land in one piece with all your faculties, you find yourself standing on a body that's small and round. It's about 10 miles across. Because the gravity is very strong, you can see over the surface. And just standing in the one spot, looking around, you can probably see 2/3 of the surface. So much is the light bent over the horizon. It's probably not healthy for another reason, because there's probably a very strong magnetic field. And in addition to the strong gravity tearing your body apart, the magnetic field and the electric field will upset all the metabolic processes in your body, which are dependent on mildly polarized molecules, and put those in a strong electric or magnetic field. So don't go there, basically.
But in your mind, you must have been there many times before. Is it a visualization that you have as an astronomer when you've made a discovery like this?
Usually the astronomer is working with figures. You have some kind of conceptual model that you're checking out to see if it's right. But a lot of the time, you're working with figures that are unimaginable. Now, actually, 10 miles is not bad, but that's small by astronomical objects, for example. So often, as professional astronomers, you're working with 10 to the power something, 10 to the 54, 10 to the power 182, huge numbers. And if you try to visualize it, you drive yourself mad. And it's one of the reasons I enjoy doing presentations to the public, because you see the jaws drop and you realize for the first time, well, afresh, not for the first time, what you've actually said. But you daren't go there as a professional, because you would literally drive yourself mad.
So these really are alien entities, the neutron star. Explain to me why they have such extreme characteristics. What is that creates them?
Our sun is one star. It's a very average star. There are stars that are quite a bit bigger, 10, 20, 30 times heavier. The Pleiades is a group of such stars. Betelgeuse in Orion is another one. And these big stars end their lives with a catastrophic explosion, which is absolutely vital for us because it's in those big stars that the nuclei of atoms of oxygen, carbon, calcium, iron are forged. And it's in the explosive death of the star that those elements get distributed and ultimately gathered up into our bodies. But during the explosion, if you like, the core of the star gets kicked against and shrunk, and it collapses way, way down to this 10-mile across body.
What do you mean by kicked against? What's
Well, you've got an explosion going whoosh, and the explosion could involve the whole star, or in this case, it could involve 95% of the star. And the central 5% or so remains, but very squashed. Because if this was it originally, you can think of the explosion as being round here, so that stuff goes out and this stuff goes in to make a collapsed body.
And when you say this is dense, it's really dense, isn't it?
It's really dense. The best analogy I have, and we, even with the analogy, suffer from big figures, is if you take a sewing thimble and you take the population of the globe, which is about 7 billion people. Teenagers love this bit. You jam the people one by one into the thimble, and when you've got all 7 billion jammed into the thimble, it weighs the same as if it was made of neutron star material. That's still a big number.
That's a big number. Someone once described to me that if you took a piece of a neutron star and dropped it on the Earth, it's so dense it would fall through the Earth. Is that a true?
I think actually the Earth will fall to it, and it will hit the deck, travelling at half the speed of light.
Wow. These are strange things.
Yeah, astronomy is real, you know.
And how common are they? Are there very many in our galaxy? Are there?
We suspect there's about 100,000 in the galaxy. We can't see all of them in the galaxy because these objects are pretty faint, and they're normally below the threshold of detection if they lie in the far half of the galaxy. We've got a reasonable census of what's in the near half of the galaxy. But yes, they must be throughout the galaxy and through other galaxies as well. And when we get big facilities like the Square Kilometre Array, we'll certainly be able to see all the ones in our galaxy, and probably some in other galaxies as well.
And how many have we found so far?
About 2,000.
And how many of those have you found yourself?
4.
And I believe they were the first 4.
They were the first 4, yes.
The most important 4.
And wasn't it good it was 4 and not 1? Because when you've just got one of something, it's a nightmare, particularly if it's something crazy like a pulsar. Yeah.
And in terms of the creation of these extraordinary pulsars, if one was formed near to the Earth, so people often talk about Betelgeuse, as you mentioned, being a star that could go supernova at some point fairly soon.
Well, on an astronomical timescale, fairly soon.
We're due one, aren't we? It's been a while.
No, we're actually not doing too badly for supernovae. We're due a good comet. We're overdue a good comet, but that's another story. But yes, Betelgeuse will go supernovae someday, but it could be thousands of years yet. Probably will be thousands of years yet. And it's showing no signs of it yet because it's still perfectly stable, and we expect it to get a bit jittery before it explodes. Yeah.
And will Betelgeuse form a neutron star? Is it likely to do that?
Yes, it is likely to do that. The only uncertainty, well, apart from uncertainties about when, is sometimes with these explosions, some of the material falls back. And if you make a neutron star too heavy, a new neutron star too heavy, it collapses to be a black hole. So it'll probably form a neutron star, and probably that won't collapse to a black hole, but you never know.
And should we be worrying about this? What would be the impact of having a neutron star that close to the Earth?
If Betelgeuse was within 25 light years, and a light year is about 10 million kilometers, if Betelgeuse was within that range, then we should get worried, because along with the explosion and the formation of the neutron star, there'll be a blast of X-rays and gamma rays, which would wipe out the Earth's atmosphere and would give us all radiation sickness. So it would probably terminate life on Earth, at least life on the surface of the Earth. But Betelgeuse is actually about 65 light years away, so it's quite well beyond the 25 that we believe is the threshold for danger. And just to reassure you, we don't know of any big star like Betelgeuse that should go supernovae within the 25 light year.
Okay. There's not a lot we could do about it if there was one either.
No, well, build some spaceships quick and go somewhere else.
Yep. Okay, we may come back to that later on in the... So, this extraordinary discovery that you made in 1967 was when the first signal was detected. Let's go back now and work our way all the way back to neutron stars and try and understand how this extraordinary picture of these phenomena was created from a muddy field in Cambridge.
In Cambridge, yes. Yes,
So
unspectacular.
You'd gone to Cambridge to start your PhD?
Yes, yes. I'd done a Bachelor of Physics degree in Glasgow, and rather to my surprise, found myself in Cambridge. And chose a project that involved looking for what were then very sexy objects called quasars. We only knew of 10 or 20, and this project was to find a lot more, and it did. I multiplied the number of known quasars by a factor of 5 or 6, so that was successful. But it involved, first of all, building your own kit, which in this case meant 2 years out in a Cambridgeshire field building what looks a bit like an agricultural frame, something like that, you know, lots and lots of wooden posts and lots of wire and cable. It was cold. It was quite heavy manual work. By the end of my PhD, I could swing a sledgehammer. And that's not normally one of the skills you get out of a PhD.
And was this enjoyable at this time? Was there a sense of kind of purpose that you felt as you kind of stood in this field, wiring? What was it? I think it was 120 miles of wire were involved in that.
Yeah. I wasn't doing that bit solo. There were about half a dozen of us. Right. And it was hard work for all of us. That's absolutely true. But, you know, you're building it for a purpose. It's going to look and find more quasars. And it's important to build it carefully so as you don't have to spend days debugging it when you try to switch it on. So, you know, we worked with intent. Okay.
Should we watch the clip just to see that field that you were working in? We've got a clip from a horizon from, I think, 1971 that we'll just watch for the next few minutes. You could play the clip.
At the Maillard Radio Observatory in Cambridge in 1967, the new instrument was perhaps the least glamorous telescope ever built. It looked like 4.5 acres of washing line. It was created for an investigation into certain special galaxies that are far across the universe. For this, it had to be extremely sensitive, so they simply covered a field with radio aerials. In fact, more than 2,000 of them. The array could not be moved to track a star. It simply rotated with the Earth, scanning continuously, night and day, across the sky. And it was to be operated full-time by one person, a girl, the graduate student who'd helped to build it, Jocelyn Bell.
We were actually using this telescope to look for quasars, because they twinkle, and this thing's specially designed to pick out twinkling things. And after we'd been running, I suppose, about a few months, I began to notice there was something slightly curious on the records. They came out as paper charts. And, of course, on these charts you could see radio sources, and unfortunately you could also see man-made interference. But there was also something that didn't quite fit either bill. It wasn't exactly a twinkling radio source, and it wasn't exactly interference either. And then we began to notice that it was coming at the same sidereal time each time. In other words, it kept pace with the stars, not with any of our man-made activities which go by the sun or by Greenwich Mean Time.
The analysis of some 3.5 miles of data took patience and persistence, but in the end, she satisfied herself that this was a star that ticks like a clock. It was beating time in periods of just over a second. What was the first reaction of her supervisor, Dr. Tony Hewish?
It's absolute nonsense. You don't believe this at all. It must be something artificial. Nothing in nature could do this, so you disbelieve it as long as you possibly can.
Everybody's first reactions were that it must be man-made. Second reactions, not really voiced very loud, were, well, perhaps it's little green men, another civilization. They could produce a man-made signal. They would be close to a star, like our sun, and they'd move around with the stars. I think perhaps being younger myself, I found it slightly easier to believe than some of the older hands at the game. But we did really spend a lot of time with that first one trying to explain it away. We wrote round to all the astronomical observatories in sort of Britain saying, have you had any program going which might possibly cause radio interference? Because, of course, the only people who keep sidereal hours, sidereal times, are astronomers. It was easier with the second one. And that was a great relief in many ways because it removed this possibility of it being little green men. Highly unlikely that several lots of little green men would be all signalling to us, all at the same frequency, all at the same time.
Later, Jocelyn Bell wrote up her work for the degree of Doctor of Philosophy. Mostly her thesis is about how the aerial system works. Almost in passing, it records one of astronomy's most exciting discoveries. This was an entirely new type of star. The hunt was now on, and everybody joined in. In a sort of galactic gold rush, the discoveries poured into the scientific papers. A name was invented, pulsars, and this pulsarium was constructed to show their location and characteristics. To see them clearly in this demonstration, they're made to flash at 1/10 of their real speed. Most of them pulse at intervals of between 1 and 3 seconds. Also, the majority of them seem to lie in the plane of, and therefore must be part of, our own galaxy.
Clapping the television or Jocelyn's contribution. It's so Heath Robinson when you look at that.
Yeah.
I mean, it's extraordinary how... What are we actually looking at when you look at that field? What is the...
Well, what you see, of course, are the 1,000-odd wooden posts, but they're not actually part of the action. They're simply to keep the electrics out of the long, wet grass, because long, wet grass is an electrical conductor and will short out any signal. So the actual antennae are up the top of the posts, and then there's wires and cables connecting up all the antennae and taking the signal back to the lab. Do you remember those old-style TV aerials that were kind of in an H shape? Well, it's a bit like one wing of the H, one stalk of the H. Each of those, there were 2,000 of those.
Wow. And it worked first time?
It worked first time it was switched on, which is very unusual. And I think it was because we had a very, very good technical assistant who wouldn't let us academics take shortcuts, and drove us mad in the process, but proved himself right in the long run.
Why did you choose radio astronomy? It's something that sort of is more abstracted than astronomy, kind of using telescopes and the kind of the experience of seeing what you're looking at so directly.
Mm-hmm. I was interested in being an astronomer from my late teens, mid-teens. And of course, like probably everybody else, I started thinking in terms of optical astronomy and spoke with some astronomers at Armagh Observatory who said, you need to be good at staying up at night. And even as a teenager, I knew I needed my sleep. And so I thought, oh God, I can't be an astronomer. And then I discovered there were these new astronomies that had opened up post-Second World War. Radio astronomy was one. X-ray astronomy was another. You do that using satellites launched, up above the Earth's atmosphere. And I decided radio astronomy was probably the better bet. So I thought if I get a good enough physics degree, I'll try and do a PhD in radio astronomy. I didn't have a problem with the visualization. Stars give out radio waves, stars give out X-rays, stars give out optical, infrared, ultraviolet, the whole gamut. And you can observe stars in any of those wave bands.
So it was a love of sleep that led to our discovery of
it's
pulsars.
my bed, yes.
That's an exclusive here this evening.
Yeah.
Well, I'm really interested to do, because I think for a lot of people, radio astronomy it doesn't have that tangibility of optical astronomy in terms of seeing
And
the
you're
phenomena.
a man whose profession depends on radio signals?
Indeed. We turn them into optical signals.
But
don't
you
we?
transmit them
we transmit
as radio.
We do.
Yeah.
I'm intrigued to work through how those blips that we saw on this huge amount of data, 3 miles of data you were looking through, how that was slowly translated into this description of a phenomena of a star as extreme and wondrous as a pulsar. So you've got the blips, that's what you've noticed.
We've noticed that there are these blips beating at about a bit over a second. And after a month, we have a second lot beating at a slightly different rate, but very, very similar.
From the same part of the sky?
No,
or
totally
from a
different part of the sky. And that's what settles the little green men hypothesis. But while you've only got one lot, it's a huge puzzle. And you slowly start deducing things. These pulses are quite fast, as you've seen on the trace. Fundamental law of physics that if something's going to change fast, it's small. So these things are small.
Let me take you back even before that. So
Right.
these blips are there. How do you know, as it sort of mentioned, this isn't something that's just an anomaly that's coming from an earthbound source? How do you know it's from somewhere far away?
Well, you don't at this stage. You're just starting with, we've seen some blips. And the first thing is you notice that it keeps its place amongst the constellations. It's often not there. This was another complication. It's only visible 1 in every 7 or 8 times you look at that bit of sky. So it's very weak and just detectable. But when it's there, it's these very clear blips, and they're quite fast. And each time you see it, it's going at the same rate. It's not getting tired. And if it's not getting tired, it means it's got big reserves of energy, so it's big. So yippee, it's small and it's big. And then you have to be a slightly better physicist and ask the question more precisely. And what we're saying is it's big in mass, but it's small in radius. I think, what the hell is that? And then somebody remembers reading a paper about a crazy new kind of star that some mad theoreticians dreamed up. And they find the paper, and it's one of the early papers about neutron stars, which are expected to be 10 miles across. But because they're only 10 miles across and small, they produce very little, shall I call it, natural radiation. They don't shine, or their shine is very, very limited, so nobody thinks they'll ever be visible and we forget about them. But they have actually been predicted. So maybe it's a neutron star. We haven't a clue how it's producing so much signal, but it is. And then fortunately I find another one, and gradually the picture builds, and you end up at the point where we published the paper. We had 1 or 2 ideas of what it was, and it ultimately boils down to being either a neutron star that's been predicted that's rotating, or a white dwarf, which is currently the most dense thing known, and is oscillating and is somehow producing shock waves and somehow producing radio signals that come in ba, 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 ba. But this one isn't a terribly satisfactory model. And the real crunch comes about 6 months later, when the pulsar in the Crab Nebula is found, and it's going with a period, it's going to about 30 hertz, 30 cycles per second, 30 pulses per second. And it's going sufficiently fast that if you measure its period to about 14 decimal places, and keep measuring its period to 14 decimal places, you can see the period's getting longer. And something like this, as it tires, goes faster. Something that's rotating as it tires goes slower. So it's a rotating neutron star. But that's a collaborative effort over a period of 6 months by a whole lot of scientists.
So when you're trying to break out from this single data set into a greater description and understanding of it, were you scanning the whole sky? How do you start the process of looking for that second sample, that second neutron star?
Well, in the midst of all this, my main thesis work was still going on, looking for more quasars. And so we're regularly scanning the sky. It just continues. 100-foot of chart paper a day piling up on my desk. And in the course of data analysis, once you know what you're looking for, it's easier to find more. So I spot a second one about a month after the first one, and I spot another 2 on the same afternoon about 3 weeks later. And at that point, my thesis advisor says, "How many more have you missed? Go back through all your old records."
And at this point, the description of what they are is you're still uncertain of the phenomenon, but
Yeah.
you know that there is a pattern emerging in the data.
Yes. We can see that they are all objects that move around with the stars. We've managed to get an estimate of the distance of the first one, which puts it within our galaxy but beyond the solar system.
Just to pick up on that, how do you know how far away they are?
If there are any radio amateurs here, you'll know what I'm talking about when I talk about a whistler. But let's suppose you are a radio amateur and you spend a lot of time in your basement at home with headphones clamped on listening to a radio set. And if there's a thunderstorm in New Zealand and a lightning strike, that goes and that produces a of radio waves which propagate round to Britain. And as they propagate round, they go past a number of electrons, which there just are in the near Earth space. And that makes the radio wave get what we call dispersed. And the high frequencies arrive before the low frequencies. And what this radio ham hears is, and for the next lightning stroke. Now, we discovered we were hearing a signal a bit like that, only it was much, much more spread out, so much slower descending note. And how fast it descends is determined by how many electrons it's come past. And so you can guess how many electrons there are in outer space and get an estimate of the distance.
And that gave you a distance of roughly what for the first
200 light years, kind of thing. Wild guess, but good enough.
Right.
That's one of the things scientists have to learn to do, is to make stabs at answers, make almost guesses, informed guesses. And you've got to go on that basis. You don't have the full data and the immediate proofs instantly. You're working your way towards it with whatever bits of data you can get and trying to keep them all in the picture at the same time.
So you have these signals, you have a confirmation of another one. You know that it's a couple of hundred light years away. It's small,
And it's
but
big.
it's big.
Yep.
Where's the next step towards it? Was it the theoretical paper coming in that then starts to put the whole picture together of a neutron star?
Yeah, I can remember the evening before I discovered the second one, going to see my thesis advisor and stumbling upon a meeting that I probably should have been part of from the beginning. It was him, the prof that headed the group, and another senior member of staff. And they were discussing, how on earth do we publish this thing? We've only got one. We're beginning to run out of tests we can do on it to get more information. What do we do? And we didn't actually solve it. And I came back into work that evening to do some more of this routine chart analysis, and that's when I found the second one and confirmed it in the middle of the night. Went out to the observatory and saw it going chuk, 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 chuk. Yeah. People say it was finding...
Was that a solitary moment?
Oh, yeah. Yeah. But that was the Eureka moment, whereas finding the first one was really so darn puzzling, and, there must be something wrong. But by a month afterwards, we've established there's nothing wrong, it's not interference, it's out in the galaxy, it's small and it's big. And what do we do now? And she finds a second one. So that's much, much better. It's some new kind of stellar population. Still don't know what, but it's something astronomical.
And what happens next?
There's a Christmas break. I go home with my fiancé-to-be. We announce our engagement. I come back on, I don't know, about the 6th of January. And Tony's been keeping the survey running for me over the Christmas holiday and piled all the charts on my desk to be analysed. And so I sit down and start analysing charts. Oh, which one's that? It's neither. It's a third one. Crikey. Make a note of it. I'll just finish this chart and then we'll come back and pass on. What? And at that point, Tony turns up. He says, "Look, Tony. Oh, Happy New Year. Look, Tony." And that's when we have the punchline, "How many more have you missed? Go back through your..."
What's the ownership of a discovery like this? You say it's a eureka moment. You've had that moment on your own, but you're also working with a team. How does that...
Well, I'm working with my supervisor. The team that built the telescope has largely evaporated. Occasionally one or two of them get hauled in for help with some of the special tests we managed to do. But it's largely Tony Hewish and I, And he's keeping an eye, but from a distance. He's fairly hands-off. And every so often I go and discuss things with him and say, this funny source, don't know what it is. Just get that job done and then we'll look at that kind of thing. So guidance like that.
And the work is published and is obviously picked up around the world. It's a major discovery. It's something that you're very much connected with and owning at that stage.
Do you see that? A girl. We wouldn't call a 24-year-old a girl today, but there was a different attitude to female scientists then.
So what was the reaction when the publication happened and all of the attention came onto the field in Cambridge?
The interviews followed a fairly predictable pattern. There'd be Tony and I, and they'd talk to Tony about the astrophysical significance of this discovery, and they wanted a bit from me about the human interest. What were my vital statistics? Would I describe my hair as blonde or brunette? Was I taller than Princess Margaret or not? And how many boyfriends did I have?
Taller than Princess Margaret? Was that the barometer of height at the time?
Well, I got a bit fed up with this, to put it mildly, and sometimes just couldn't remember. So then they'd prompt me,
How did you deal with that? So you're 25, 26 at this stage. It's a huge discovery. You've been absolutely fundamental in happening, and they're asking you ridiculous questions. What do you do?
Yes. I found it very difficult. I'm at the stage where I haven't finished my PhD. I cannot afford to fall out with the laboratory or with any senior scientist. I would love to say something really rude and sharp and clever, but I daren't. But it's incredibly excruciating embarrassing. And the photographers would say, "Could I undo some more buttons, please, for the photograph?" So, girl.
Looking back, do you replay it in your head? Do you have regrets about how that played out? Or was it an inevitable part of the way, unfortunately, that people were behaving at that time?
It was part of the sort of prevailing sexism of the time. I do very much regret it. I've thought back on a number of aspects of it, and I think actually I played the whole thing fairly well, particularly given I was pretty young at the stage. I was in a very vulnerable position, both then and later on with the Nobel issue, because I still haven't got a tenured job. I badly need references from, Cambridge academics, and I cannot afford to fall out with them, but I do have some integrity and would like to tell the truth. So,
You mentioned the Nobel, which infamously you weren't included on. Is this something that you've left behind now? Is it something you feel drags with you? How does that sit?
Well, every so often interviewers ask questions about it as if it were important. Yes, Andrew.
I'm asking you if it's still important.
No, I don't think it is. And I think actually it's played out very well, because if you don't get a Nobel Prize And it's 1973 when feminism is arriving, and there's a whole cohort of people of your age who think you should have been included. You find that as you go through life, you get all sorts of other prizes and awards and honours. And it's far more fun, because if somebody gives you a Nobel Prize, nobody else will give you anything, because they don't reckon they can match the Nobel. So I have a party almost every year. And that's playing out a lot better than a spectacular week in Stockholm, thank you.
Are you confident that it wouldn't happen today, that we have truly moved on from that era?
There was it was either 1993 or 1994, another Nobel Prize given for another pulsar discovery, and it went to the supervisor and his student. And they invited me along as their guest. It's far more fun being a guest at a Nobel ceremony than being a recipient, I can tell you. Yes.
So we are fully beyond that now. That's...
Well, it keeps coming up. You know, I do keep seriously being asked questions about it. I had a curious sort of twinge last October when the Peace Prize was announced. Do you remember that it went to an Indian woman who'd worked on women's rights and that Pakistani girl, Malala? Now, she was 17 or 18 at the time, and she suddenly got £100,000 or something like that. I hope she's had very, very good advice, because there'll be people after her money, people wanting her endorsement of their crackpot schemes, people wanting her to appear there and everywhere. And I bet she's had a whole load of marriage proposals as well. And it's really tough for a young person to handle that kind of thing. So, yeah.
Regardless of the Nobel, though, you were tough in your application to that work at Cambridge at that time. I mean, it required a tenacity,
yes,
and a strength.
Yeah, and that's been one of my characteristics, I think. I can remember school teachers remarking on how I didn't give up easily. But there was another element, I think, to the Cambridge thing. I mentioned that I'd done my first degree in Glasgow and I'd come from Northern Ireland, so rather to my surprise, I found myself in Cambridge to do this PhD, and I'm clearly a provincial, you know, I'm from the Celtic fringe, from the sticks. And Cambridge is a mecca of learning, and they know it. It's been said more recently of Cambridge astronomers that they're frequently in error, but never in doubt. And I think that was probably true then as well, only I didn't realise they were frequently in error. They just seemed to be absolutely brilliant. And I thought, gee, I'm not up to this. You know, they've made a mistake admitting me. This is what we now call imposter syndrome. And in a bad case, the person will go on, whoa, yes, I shouldn't be here. They're going to discover they've made a mistake admitting me. They're going to throw me out. I'd better leave before they throw me out. And in Oxford, we do have people leaving. It applies to less confident people, particularly women, but also some men. But I'm a bit of a fighter, so I said, okay, they've probably made a mistake admitting me. They're going to discover it. They're going to throw me out at some point. But until then, I will work as hard and as thoroughly as I possibly can so that when they throw me out, I won't have a guilty conscience. So I was absolutely determined to understand every quirk of that radio telescope and receivers. So I was chasing every anomaly. And most of them are mundane. That one wasn't.
Would it be almost right to just say it was insecurity that was driving you, and tenacity,
yes,
rather than curiosity in terms of pushing you through the work that you were doing?
Yes, I mean, I wanted to do a PhD for reasons of curiosity, but the actual execution of the PhD required tenacity and so on, yeah.
And where do you think that combination of tenacity and curiosity formed? Was that part of your schooling? Was it your upbringing at home? Was it where did it come from?
I started life in rural Northern Ireland, and vivid memories of my first week in secondary school, which was by and large fantastic. You know, you get to do all these new subjects and you move from classroom to classroom and you've got more than one teacher. It's a big improvement on primary school. But I remember the Wednesday of that first week, because a message went round the class that on Wednesday afternoon the girls were to go to such and such a place and the boys to a different place. It's sport, that's why they're separating us. Girls went to the domestic science room and the boys to the science lab. No discussion. That's where you went. That was your role in life. And my parents had promised me that when I got to secondary school I'd get to do some science, so I sort of said to the domestic science teacher, "Don't think I should be here. Well, just stay here for this afternoon, dear." I told my parents that evening and they read the Riot Act, as did the local GP who had a daughter in my class, as did the parents and one other girl. And when the science class next met, there were 3 girls and all the boys. And we 3 girls had to sit right under the teacher's nose because clearly we were dynamite or something. And I came top of the class at the end of that first term.
So science was it was important in your family when you were growing up then? That wasn't, because that's a forceful thing that your parents did in terms of insisting that happen.
Yeah, yeah. This is incidentally close to Sputnik, the first ever artificial satellite, which the Soviet Union launched, and that produced considerable shock in both Britain and USA, because we all assumed we were technologically superior to the Soviet Union, but we couldn't launch a satellite into space. So there was, at least probably shortly after that, great emphasis on anybody who could do science doing science, because the country needed scientists.
But you fought your way through some horrendous sexism all the way through your career, including Glasgow and Jodrell, I've read about. You had you didn't apply to do your PhD at Jodrell, that's correct?
Yes, that was where I was first intending to go, because I had worked there the previous summer. But they lost the application down the back of the desk. I think actually it was genuine incompetence, but I read it as they're not taking a woman, because the word amongst the grad students there the previous summer was that they wouldn't take a woman.
And have we truly moved beyond that now in all of the sciences, in the physical sciences as well as the biological sciences?
No. I hope we're getting better, but it's pretty slow progress. There are more women at the junior stages in academic life, and by the time you get to the professoriate, there are very few. Even in biology, where 70% of an undergraduate class will be female, the professoriate is still predominantly male. So there are still considerable issues. Yeah.
And what will change that?
I think it's beginning to change quite fast. Thanks largely to Dame Sally Davis, who's the Medical Officer for Health for England and Wales. She controls quite a lot of funding for research, and she has said to departments that might apply to her funds that they can't even apply unless they demonstrate themselves to be women-friendly departments by holding a particular award called Athena Swan. I helped set up Athena Swan quite a few years before, and it did okay, but then suddenly everybody needed Athena Swan. Money speaks. I'm afraid, the way nothing else will speak.
Right. And that's the lever for change?
In Britain it seems to be, yeah.
Okay. Well, we've almost run our time in terms of my questions, but we're going to open up to questions in a second. There's one question I just want to ask you at the end. Very famously, the signal was called LGM, Little Green Men, when you first discovered it. And I'm just wondering whether you would have preferred, looking back now, to discover a pulsar, to discover the first SETI-type signal indicating some kind of intelligent life form. Which way would you have preferred it to go?
Oh, I was relieved it wasn't Little Green Men, because there would have been such a hullabaloo that I would not have been able to complete my thesis. I'd only 6 months of funding left, and it was getting a bit tight, so
okay.
Very glad.
Pragmatic answer.
Yeah.
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 And the significance of those papers that came out of the lab
Do they still exist now, or were they sort of...
The chart recordings?
Yeah, with the initial markings. And
one or two crucial ones have been preserved and are in Churchill College, Cambridge archives. But you can't preserve 3 miles of paper chart.
More questions?
Good evening. Thank you so much for being here. A very technical question, and excuse my ignorance because I'm more accustomed to optical astronomy. If you've got your radio telescope on a patch of Earth as the Earth turns and it's pointing straight up, how do you scan different parts of the sky, or do you just have to wait till it's 6 months later and you're naturally pointing at a different part of the sky, if that question makes sense?
You're not actually pointing at a different part of the sky 6 months later. It's the same sky, it's just whether it's in the night or day sky. And with radio astronomy, there isn't night and day because the sun doesn't dominate the sky in the same way. You'll have seen on the film clip all those wooden posts. Telescope's very firmly rooted in the Earth, and it's orientated to look due south. But what we can do is, with electrical phasing, swing the beam up or down. So you do a scan of that strip of sky, and the next day a scan of that, and that, and that, and so on. So that's basically how it works.
Questions, yeah.
Hello. I'm not a scientist, I'm just a fan. So I just wondered about your life in general, because it's just amazing. And I just wondered whether how much work you were actually doing now, whether you enjoyed the good old days when you could get your hands dirty in a field, or the days now when you're interviewed by a man from the BBC.
Well, I'm officially retired, which actually means I don't get paid for what I do, but that's okay. I took retirement a year or two early because I was getting lots of wonderful invitations to go places and speak. And I thought if I keep refusing these, they'll dry up. So I have been largely, quite a lot of my time kind of globe-trotting over the last 10 years. I also do quite a lot of committee work as well as a lot of public lectures. And it's a good mix. I'm here in Edinburgh quite a lot at the moment because I'm president of the Royal Society of Edinburgh. More committees, more emails, And I'm lucky enough to still have good health, so that's great. So I'm very much enjoying it, but I am no longer doing my own research, and I do very little regular teaching, although I regard doing a public lecture as a form of teaching. It's just you've got a different class each time, different set of people.
There's another question at the back there.
Good evening, Dame Jocelyn. A question, it's not an academic question, but when I read your papers and see you on television, I always end up thinking the same thing. I lived in Cambridge when you were at Cambridge. Did you ever meet Prince Charles at Cambridge? Because he was there around the same time, was he not?
No, I didn't meet him, and I think he was a little bit after me, because I think he's about 10 years younger.
All right.
But I still had contacts with Cambridge when he was there, sure.
Thank you.
I'm sure he would have slung the sledgehammer if he'd been there to help out with the...
Maybe.
Next gentleman there.
Jocelyn, it seems to me that what you described could be called little science, very much working on your own, occasionally with your supervisor, and when you found the second pulsar, you were on your own that night. Has there been a change in the kind of the way that science is being conducted from little to big science in your area? Is it now bureaucratic teams with extensive division of labour, etc., very different experience of conducting science? Does that accurately describe a change in your field?
One of the very big changes, of course, is the introduction of computers. There'd be nobody scanning 3 miles of paper chart these days, but they'd probably have 3 gigabytes of data to handle on their computer. There are certainly some projects that are very, very big, and have large numbers of collaborators with their own very interesting issues about how you run them and how the young people get credit for what they do and who's in charge and who's not in charge and all that kind of thing. But there are also people who refuse to join these big consortia and say, I'm hanging on to my 2-meter telescope. My grad student, is going to do this, this, and this. So there is both, but probably the majority are now in considerably bigger collaborations, yes.
In front.
Sorry, speechless. You're an absolute inspiration, and I can't imagine how hard it must have been to be the woman or the girl at the time. Mm-hmm. God, that made me cringe in the video. Mm-hmm. But what was it like actually in the classes? Because it's one thing when the media is treating you as the girl, but I'm assuming it wasn't much different in the actual environment that you had to power through.
There was still the assumption that when women married, they stopped work. Because if a married woman had to work, it was shameful. It meant her husband couldn't earn enough to keep her. That was bad. And mothers certainly didn't work because it was proven that if mothers worked, the kids were delinquent. So it was very, very hard to keep going, particularly after the PhD. And it was very makeshift, my career, succession of jobs at that stage. And that to some extent influenced the way I was treated in the lab, particularly because I was stupid enough to wear my engagement ring into the lab. And that really was stupid. But I was very proud of that ring. So yeah.
If you had to choose a PhD topic today, what might it be?
There's a lot of very exciting things around in astronomy at the moment with, I think, a great surge of discoveries coming. One of the areas of astronomy that we have neglected until very recently in the race to see deeper and deeper into space is studying things that are time variable. Basically what we've done is we have stared and stared and stared and stared with a very, very long exposure, 8-hour-long exposures to get those distant galaxies. And something here has gone wee. And because we've been had an 8-hour exposure, we've lost the wee. But now, with the development of better digital cameras and a lot more computing, what you can do is you can take a frame, a few minutes later, take a frame, take a frame, take a frame. And if you want to get that very, very faint galaxy, you just stack all the frames together. But it also has the advantage that if something goes, yoo-hoo, you see it. And this is really just beginning. It's called transient astronomy, or our dynamic sky. Not to be confused with our dynamic Earth here in Edinburgh. And I think we're going to find a lot of things doing, at us, which would be really interesting, for example.
So that's a quick question before we finish off a couple of questions. So what do you think, what are the other big discoveries out there that kind of you see coming down the track? What's left to find out?
Well, there are a lot of predictable discoveries as well as the less predictable one, that I've just talked about. We're finding a lot of planets round other stars, extrasolar planets. And the people that work in that field say within the next 100 years, we're going to have evidence of life on one or more of those planets. Now, it might not be intelligent life. It might be simple cellular or microbial, but we're going to have evidence of life. That's a huge milestone for humanity. And humanity, I think, hasn't really cottoned onto this yet, to be honest.
What would that evidence be? It would be a signature of some type, would it?
Well, what we're beginning to be... I need a visual aid.
So I need to hold something, right?
Big star, planet going round it, okay? You take a picture like that and a picture like that, and you take the difference, which gives you this. If you've got the spectra, the rainbow, so to speak, you can tell what the atmosphere of this planet's like. And there may be some of the special chemical signatures like methane, oxygen, or even just saying the atmosphere of this planet is out of chemical equilibrium. It's driven out of chemical equilibrium by biological activity on the surface of the planet. So those are the kind of things you're looking for. Yeah.
So it's the answer to the question, are we alone, may be
no.
A chemical signature.
Yeah, yes. That's bound to be the way it is, I think. The chances of picking up signals from them, A, assumes intelligent life and, you know, we know where they are and all that kind of thing. I think the atmospheric chemistry of a planet is likely to be the way we'll find evidence of life.
So your answer to the question, are we alone, is?
I very much doubt it. But I do accept that we may not find intelligent life on some of these exoplanets for quite a while, even if we find evidence of biological activity.
Okay. There's a few more questions before we finish. Just there.
Hi, I was just wondering, like, when you're applying for jobs or applying to do your PhD, do you feel you were judged on your appearance more than you would have been if you were a man?
That is certainly a factor because all of us reach a very quick judgment on people. They say that about the first 30 seconds actually settles an interview, which is a little scary. Now, we are learning that goes on and we can to some extent compensate for it. We are also learning that men and women have what we call unconscious bias, which tends to assume that the male is more authoritative than the female. And this is something that we are now learning to keep track of. It's fairly new learning this, but we're learning to keep track of it when we're dealing with interviews or applications for promotion or things like that. But the world is not symmetric for the male and the female, I think is absolutely true. I'm afraid. Yeah.
Time for a couple more. We've got one at the back there. I don't think you've asked a question yet.
Hi. In light of what you said about transient astronomy, there was an article in New Scientist a couple of weeks ago about these fast radio bursts
yes.
and the dispersion ratio, consistent
yes.
ratio in the dispersion
yes.
of those bursts. And I just wondered if you had any thoughts on that and whether it could be pulsar related or a similar kind of astronomical object.
So just to fill other people in briefly, the pulsar radio astronomers have found single pulses, bursts, from various bits of the sky, no repeats, nothing there. And when they look at this whistle, it's a very slow whistle, and the implication is that these things are way beyond our galaxy. And then somebody looked at these whistles, the dispersion rate, and said, hey, there's 10 of these objects now known. Do you know, those dispersion rates are all multiples of 187.5. God only knows why 187.5, but you know, they are all multiples of. And this looks a bit artificial. So the press went to town and said, aliens, predictably. I think it may the debate is on, and the debate is raging, but it could be something like military satellites that, you know, scan at this rate. And of course, their existence will be denied, but it could be. I think basically we need more data. An eminent US astronomer, Sri Kulkarni, has laid a bet of $1,000 that these things are not astronomical. And a number of people are interested in taking him up because they're not sure he's right. Too early to have the last word, but very interesting.
I wonder if there's a 24-year-old that he's arguing with.
Could be. There's a lot of very able young people in astrophysics these days.
We've got time for one or two more questions. Let's have a look. Yeah, just in the row there.
Just as a fellow, I suppose, female in a male-dominated, I'm a civil engineer, so it's always lovely. I've heard you speaking before, so it's always lovely to hear you speak. But I was just wondering on like a personal note or professional note, what do you regard as your proudest achievement? Is it in your studies, or is it your work now that you're doing representing women in STEM or being a role model for women, or even on a personal note?
I wonder. Obviously, discovery of pulsars is quite a major thing. I'm also quite proud of a piece of work I did for the Quakers, and this is totally different, but I'm proud of it, on suffering and the role of the wounded, particularly the wounded who won't heal, so the ministry of the wounded. I think I did important work there. I had a very interesting time facilitating a meeting where Pluto was declassified as a planet. That was a very interesting exercise in handling a body of about 1,000 astronomers who'd been got into a very scratchy mood. And I had to kind of get them going again and get a decision. So I'm quite proud of how I handled that. So those are 3 very different kinds of things. Thank you for the question.
It hasn't dented the excitement of New Horizons arriving, has it?
No, the New Horizons people did finally adapt, having initially been really against this reclassification. Suddenly realized they could pitch their mission as the first mission to the nearest and most accessible dwarf planet. And it gets there in July this year.
It's exciting, isn't it?
Yeah, mid-July.
It's already found 4 or 5 moons around?
Oh, Hubble found those.
Hubble found those?
Yes,
right.
Yeah, that's right. 5 moons at the last time I looked. Right. They may well find more.
One more question and then we're going to wrap up. Was there one lurking over here that someone hadn't asked before?
Yeah.
Hi, I was going to ask for female scientists or PhD students now, what word of advice would you give to them?
Hang in there. Don't give up too easily. I think that applies in many areas of life, but I think it's probably particularly true in getting through the PhD.
Okay. Well, I was just going to say, to finish off, if that's okay, I said at the beginning, it's an absolute privilege to have the chance to interview you and talk to you this evening, and I'm sure you've all felt exactly the same as me, really, so I'm sure you join me in thanking Jocelyn very, very much for this evening.
Yeah. Thank you very much. Thank you very much, too. Very good.